Okay, let's continue a little bit with units and let's get through this chapter. So we have basically 4 fundamental units. They are distance that we read in meters, there's time that we read in seconds, and then there's mass that we read in grams. So the meter is a lowercase m, the second is a lowercase s, and the gram is a lowercase g. And on Wednesday, which class did I do on Wednesday? I did time. I did temperature.
No, temperatures related, and we haven't done volume.
Oh, okay.
No sin of running it again.
All right. Well, time is a little bit different. Time is measured in seconds. It's the only one there that is decimal, because minutes are not decimal. They have 60 seconds in them. And hours are not decimal. They have 60 minutes in them. And days are not decimal, and months are irregular. And we don't count anything up. Like a multiple of 1,000 seconds is not a kilosecond. I mean, technically it is, but nobody says that. But we do go down. So seconds get divided into milliseconds, which get divided into microseconds, which then 1,000 microseconds is a nanosecond. And 1,000 nanoseconds is a picosecond. So if we divide by 1,000, we get a millisecond. I didn't do this on Wednesday?
Yeah.
Good. Somebody just told me I didn't. All right.
No, we didn't.
Blah, blah, blah. So you know that. So we did time, and we did mass or distance.
We haven't done temperature.
Yeah. Okay, great. The one thing that we didn't talk about, mass, though I'm fairly confident, is, so mass is the same thing. We have grams, goes down to 1,000, by 1,000 makes me a milligram, and if I go up by 1,000 makes a kilogram, and that K now gets uppercase. It turns out, and it's of no consequence, that it's the kilogram that is actually the Standard Institute unit. The Standard Institute unit you would think would be the gram, because that's the underlying quantity, but they use kilograms. And there is a good reason for that. There's a block of metal that is exactly 1 kilogram, I believe it's in France, and we derive everything from that. The other thing that comes out of this is that the word mass and the word weight are almost interchangeable. Mass is a representation of how much matter is actually stuffed inside your sample. So if we were going to measure the mass of this pen, we would ultimately be measuring how many atoms are inside that pen, because atoms have mass in relationship to where they are on the periodic table. Okay. Weight would be exactly the same thing. We would put it on a balance, on a scale, and we would weigh its weight, which would be equal to its mass. So for most of us, that doesn't matter. There is no distinction between mass and weight, and yet those are 2 separate names, and they have 2 different meanings. Because what weight is the physical representation of that mass being pulled downwards by gravity to the planet's surface. So when we weigh something, we put it on a balance, and gravity pulls it down. So we can put a little spring underneath there with a detector, and we can measure how hard that spring gets compressed, and we can convert that into a weight. So, unless you're planning on leaving the planet, weight equals mass. However, if you do leave the planet, weight is not mass at all. If the space shuttle weighs, total made up number, 5,000 tons, when it's on the runway, its mass is 5,000 tons. When it's in space, its weight is 0. It has no weight. It's floating free without gravity. But what's its mass? 5,000 tons. Okay. So outside of the experience of the gravitational field at the surface, technically even probably at sea level, mass and weight are the same thing. But once you deviate away from that, mass is universal. Weight changes from place to place. And then that leaves us with temperature. We had said earlier that time was going to be given a symbol lowercase t. Temperature is given symbol uppercase T. And it comes in 2 flavors. There are 2 scales for temperature. And the first is named after Lord Kelvin, and it contains only positive numbers. And this is why we use it. Go back a couple of hundred years, you see this in France, you see it also in England, for slightly different reasons. Round about the time of the French Revolution, the French were incredibly concerned about taxation. They were very, very concerned that people were going to pay their fair share. And so, over the course of time, they developed very precise instruments of measurement. And then that paid off as a boom of, scientific discovery. I can now measure down to these little tiny things. In Britain, they were concerned about making whiskey. And that meant that you needed a really good thermometer. And Kelvin's thermometers were the best. And so we've named this after him. So this is going to be a scale that runs from 0 up to, let's pretend it's infinity. There is a value at which you're not going to really be able to heat anything anymore, because heat translates as kinetic energy. That's the energy associated with motion. And if you give your particles so much energy that they have so much motion, then they end up being so far away from each other so rapidly that we can now not give them any more energy. So there is an upper limit, but it's going to be astronomical. There is, however, a lower limit. And here's how that makes sense. If you take a solid, and solids have atoms that are close to each other, almost touching. The atoms are close. And we give them heat energy. And again, heat energy is kinetic energy. That's the energy associated with motion. They're now going to start to shake and vibrate and rattle, and ultimately they will rattle loose of each other. And now they start to be fluid. You just melted your solid and made a liquid. And now those atoms are floating around, and if you continue to give them energy, then they get so much energy that they leave the vessel, and they go their own separate ways in 3 dimensions. I just made a gas. I boiled the liquid. So heating a solid makes it melt. Heating a liquid makes it boil. I go from solid to liquid to gas. Let's do that backwards. If I take a gas sample with some particles in it and I cool it down, I deprive it of energy, they slow down, they bump into one another, they lose their kinetic energy, they coalesce, but they're still moving, so they're still fluid. Let's cool them down. they now lose so much motion energy that they turn back into being solids and they just shake. If you cool them, they stop. At which point, you cannot deprive this sample of any more energy. It's given up all the kinetic energy that it had to give. Therefore, it cannot get any colder. And so the Kelvin scale has an absolute 0. Here is where all molecular motion ceases. Cannot give out any more energy because there's nothing left to give. Okay? All right, my other scale is called Celsius. And Kelvin has units K. Celsius has units degrees C. We use degrees for Celsius, but just the absolute value for Kelvin. And Celsius is a really good scale because it works on a good range of our understanding. 0 degrees Celsius is set to the freezing point of water. And 100 degrees Celsius is set to the boiling point of water. And between 0 and 100 is pretty much all we need. I mean, there are occasionally times, if you live somewhere irrational, like Michigan. I lived in Michigan for 11 years. Where that value goes below 0. Humans aren't supposed to live there. But this really is most of our experience. So it's a really good scale, but we cannot use it in most science calculations. The reason being that that number can go negative. And so really dumb things like, if I told you that the volume of a sample is proportional, the little alpha means proportional to, not equal to, but proportional to. There's some other thing going on. To its temperature. When you heat something and it melts, and then you heat it some more, it expands. You probably learned that in middle school science. Hot things occupy more space than cold things. There's an expansion that comes with temperature. So what if my temperature was minus 10 degrees Celsius? That would mean that my volume would also have to be negative. Now a volume is a three-dimensional space. It's a distance times a distance times a distance. Has to be positive. There's no way, I can't imagine a negative volume. My brain's not powerful enough to do that. So that's impossible, which is why we have the Kelvin scale. Our mathematics works with the Kelvin scale. But Celsius is a great scale because it runs from 0 to 100, and that's nice. And it's got boiling water at 100 and freezing water at 0. The other thing that's really good is that Kelvin and Celsius work on the same increment. That a 1 degree change in Kelvin is equal to a 1 degree change in Celsius. So these two are completely interchangeable between one another. That value of absolute 0 for Celsius is negative 273 degrees Celsius. There's actually a little decimal in there, 0.15, but this will do. For us, this will do. So knowing that those two scales run in parallel, on the Kelvin scale, where does water freeze? 273. 273 Kelvin. You have to say the number, and then you have to tell me what the units are. Because a number without units is meaningless. So at what temperature in Kelvin does water boil? 373. It's 100 degrees up. This is really going to work for us. Did you all see that KView have put their weather cam on Concordia's campus? Yeah, and tonight when they do the weather report, we'll get a nice shot of something or other from here. And of course, the weather report will report today's temperature incorrectly, because these are the only two scales. There is no other scale. There is no other scale. However many countries there are in the world, pick one at random, and then imaginarily make a phone call to any member of the populace in that country and ask them what their temperature was today. Not a single one of them is going to give you an answer using the temperature scale that the television weatherman or weather person will tell you tonight, because nobody in the rest of the world, in any country, uses that scale. I'm not even going to say its name. We don't use it. It's not friendly. At what temperature, using that other named scale, unnamed scale, water freeze?
Negative
32.
And it boils at
212.
and the gap between those two numbers is?
180. Yeah, 180.
Doesn't fit. We don't use it. Now, unless you're holding on to some kind of classic car for a reason, you're all carrying, well, first of all, you're all carrying around massively networked personal computers in your pocket. You can easily tell your phone to start telling you what the temperature is in Celsius. It will not take you long to adjust. It will take you a day of, oh, it's in the 20s, that's kind of nice. It's in the 30s, that's hot, because body temperature is like 38. It's in the 40s, yeah, that's really super hot. 70 is human pain threshold. So I do this in the lab all the time. Somebody will say, is this hot enough? And I'll touch it. No, keep heating it. Because if it's painful, I know it's at least 70 degrees Celsius. Don't touch the hot glass where it'll happen. Don't do that. Okay. That ultimately leads us to derived units. And derived units are everything else. They consist of the previous units that we've seen in combination. And probably the one that should be top of the list is one that feels like a fundamental unit, but isn't. Feels like it because we talk about volume all the time. Your lab procedures take this many milliliters of this and mix it with that many milliliters of that and see what happens. But volume is just a representation three-dimensional space. Which means it's a distance times a distance times a distance. Distance was my fundamental unit, and I can break volume down into being some kind of subdivision of that. Now, if the height turns out to be 10 millimeters, and the depth of my cube turns out to be 10 millimeters, and the width of my cube turns out to be 10 millimeters, and what I end up with is a volume of 1 milliliter. Now, milliliters can sometimes go hidden because they're described as something else. We specifically didn't mention it but didn't write it down, that between a meter and a millimeter there was a thing lurking in there called a centimeter. And a centimeter is used because a meter's kind of big and a millimeter's really, really tiny. And a centimeter is somewhere in the middle, like that. It's about a centimeter. 10 millimeters is 1 centimeter. So this millimeter right here, milliliter rather, is 1 cubic centimeter. So milliliters, if you read the glassware in the lab, sometimes it's written as cubic centimeters. Sometimes it's written as cc. And we've already, I mean, we should be metric by now. Come on, I mean, England, who are obstinate people, have been completely metric for a long, long time. The only thing that they wouldn't give up was a pint, because you sell beer in pints, and they would fight you if you tried to change that. But guess what? The American pint and the English pint aren't even the same thing. How many fluid ounces in a pint?
6 here or there.
16 here, 20 there. So it's not even the same thing. So this is just nonsense. We should all be metric. Your cars are metric, whether you think they are or not. You all know what the displacement of your engine is in liters. Anybody that has a motorcycle knows what its displacement is in cc, cubic centimeters. So it's just the same as milliliters. Okay. Now that we know what volume is, there's a couple of other ones here as well. Anything that is a rate. A rate is some other unit per unit time, which could be miles per hour. We would never allow that because miles are not metric and neither are hours. But there you go, miles per hour. That would be an example of a rate. If you had to park somewhere downtown, it might be $25 per day. That's a rate. It's an amount per some unit time. Our rate of speed or velocity that we use is meters per second, because both of those are metric, which is meters per second. Now, we can disassemble that and put it back together again. A little bit of algebra coming up. Because meters per second is also the same as saying meters times per second. 1/2, the reciprocal of seconds. And 1/, any number, is the same as raising that number to the power of -1. Now, there's no real good reason why we do this, other than when you write in text, it means that we don't have to indent the line by dropping another letter lower. It means that all of this can go on one line, because your computer and your typewriter can handle superscripts. Okay. So meters per second is the same as meters times 1/2, and 1/, any number, is that number raised to the power of -1. Just alerting you, because this is going to come back. Okay, density. Density is mass per unit volume. And this one turns out to be very useful chemically, because pure materials have characteristic densities. Density is actually a very, very ancient, you can go back a couple of thousand years and find evidence for this, that pure materials have values of density that is characteristic of their purity. So this density is given symbol D, to lowercase d, is equal to lowercase m divided by uppercase V. And that is normally going to be in grams per milliliter. Not always, but normally in grams per milliliter. Sometimes you'll see it be in kilograms per liter. But because a kilogram is 1,000 grams, and a liter is 1,000 milliliters, the kilogram per liter is exactly the same as grams per milliliter. It's just the difference between chemists who work in small volumes versus engineers who work on a large scale. So if you read anything that was written by an engineer, it's going to say kilograms per liter. And if it's written by a scientist, it'll say grams per milliliter. Same thing, same number. And density, as I said, is a characteristic value for pure materials. So here's things that we know. The density of gold is given symbol uppercase A, lowercase u. We have a periodic table. There's gold right there. Now, it turns out there's quite a few elements on the periodic table. We've now filled in these 118 and above. There's a little diagonal line, that's lead right there. There's a little diagonal line that goes this way, and everything to the left of it, which is most everything, is a metal. Gold is a metal, and it's right there. It's a heavy metal. And we discovered a long, long time ago that the density of the metal, who's given symbol AU for our room, is 19.3 grams per milliliter. Now, gold is very, very stable, which means it's easy to find it just naturally occurring in nature. You can find it, as nuggets. So its name doesn't follow the trend that most of the other names of the metals do. lithium, sodium, potassium, rubidium, cesium, francium, radium, barium, strontium, calcium, magnesium, beryllium. You're getting the trend. Scandium, titanium, vanadium, chromium. They all end in ium. Metals are going to do a thing called oxidation where they throw their electrons away and they end up being positively charged. And ium is the clue that what you're looking at is positively charged. And the metals do that. Rhenium and osmium. But if you're a very old metal, like iron, then you have a name that doesn't follow that trend. So iron and gold and lead don't follow that trend. So the other one I'm going to write up on the board is that one right there. That is Al. This is a very light metal. That is aluminum. Aluminum is spelled incorrectly. There's nothing that we can do about it right now. Because how do the other nations of the world pronounce aluminum?
Aluminium.
Aluminium. And how does that end? Ium, which tells us we're doing it wrong. When I say we, I mean you. You're doing it wrong. Now, when it comes time to a quiz or a test where I say, give me the exact spelling of the element whose symbol is Al, if you think it's cute that you write down aluminium, you're going to get graded incorrectly. Because here, the spelling is aluminum. I teach this same course in another country, and those roles would be reversed. Okay? Ium tells me it's a metal, it's going to go positive. It fell off somewhere. 2.7. Okay? So, here we go. I have two containers of nearly the same size. They're very, very, very similar. If one of those was full to the top with aluminum powder, and the other one was filled to the top with gold powder, gold dust, aluminum dust, and you blindfold me and you say, whichever one you pick up and you want to keep is yours. This one with the gold in it is going to weigh a lot more than that one because they have the same volume. And at the same volume, this one weighs 19 to 3. It's like 19 to 3. This weighs a lot more. So people noticed that. They noticed that very, very early on. The concept of the atom goes to ancient Greece. And then noticing, and then people were working with metals. So they had to have this understanding of, if today I'm working with copper, I know it's going to be different than yesterday when I worked with silver, which was different than the day before when I worked with gold. They all feel different. If I've got we've got a coin that is a copper coin and a coin that is a gold coin, and they're the same size, this one weighs more than that one. Right? The older people weren't dummies. They had it figured out too. So, if somebody gave me a little tiny cube, it was 1 centimeter by 1 centimeter by 1 centimeter, and they said, can you tell me if that's made out of gold? All right, so I would get my ruler or a caliper and I would measure, yep, that's 1 centimeter by 1 centimeter by 1 centimeter. That's definitely 1 milliliter of volume. And then I would go to a scale, we don't have any out in this room, and I would plop it on there. And if it came out and told me that that cube weighed 19.3 grams, you'd get the thumbs up. That's truly gold. And if it wasn't, then it isn't. It's something else. Which then leads us to what to do when faced with the problem of identifying something's purity without destroying it. Because if I gave you a great big cylinder and I said, somebody just sold me this for $100 and they tell me that's pure gold, okay? Prove to me that it is. Well, if you cut it in half, you could cut it open and look inside and say, well, no, it's lead with just a little bit of gold on the outside. You could prove it that way. But, okay, so, or if it's a straight geometric shape, you could approximate, because I know what this circumference is right here, and I know its height, so I can figure out its volume mathematically. But what if it's an irregular shape? What if Steven Spielberg gave me an Oscar, and in doing so, did a favor for him. He did a favor for Steven Spielberg. He gave you his Oscar, and while he's doing a good job, you've all done such a great job. Here's my Oscar. Take Monday off. And he tells you it's solid gold. You would wonder, are Oscars now, are they really made of solid gold? You could prove it by chopping it in half and looking at what's on the inside. But now you would have killed its value, right? So this problem was proposed to Archimedes several thousand years ago, where a king of some description came to him and said, I have been gifted this statue, and I'm told that it's made of solid gold, and I need you to prove that it is. That's a statue, so it's an irregular shape. I can't measure it and know what its volume is. Can't know what its volume is. All I can do is measure what its weight is, but that's not going to tell me if it's gold or not, because it's an irregular shape. And if I chop it in half, then the next time the king of Persia stops by and says, hey, what's that statue I gave you? Then that's going to be a political incident. And if the other king lied to the first king saying this is completely gold, then that's a political incident. So this needs to get solved. Do you know how we did it? You take a tub, a big one, and you completely fill it right up to the brim with water. And then you take your irregular shaped statue, with a smiley face, and he's holding on to whatever now. Kind of holding a, it's not a sword. What's he holding? Okay. So here's my Oscar, Mr. Spielberg. Okay. And you immerse it. Now outside of your big bucket, you put another bigger bucket. And when the statue falls to the bottom, there's Oscar, water is displaced. And the volume that gets displaced, of course, has to be exactly equal to the volume of the statue. So now you've collected some water in this bottom bucket, you siphon it out, and you measure. What we have today are things called graduated cylinders. They have little marks up the side, and you measure out how many milliliters of water. So now I know what its volume is, I put it on its scale, and I know what its mass is. Mass divided by volume equals my magic number, and if it's not 19.3, then it's not pure gold, and international incidents ensue. That is Archimedes' displacement of volume. It's a couple of thousand years old. The rumor being that Archimedes was so completely stressed by this task, and he couldn't figure out an answer for it. He was very, very concerned that it would be the end of his livelihood as being the smart guy. He went home and his wife had drawn a hot bath for him, and when he got in the bath, the water left the bathtub and he went, I figured it out. And then he allegedly ran through the streets of Athens naked, shouting, Eureka! I have found it. I've discovered the answer to my problem. Okay. Volume, density. Oh, here we go. So I put on the little pre-test this. That if density is mass divided by volume, I'm always going to enter that calculation knowing two of the numbers. But what if it's the other number that I'm trying to find out? Because all the densities for every pure material, they're already written down. They're already in a textbook, in a reference book, or now on a website somewhere. So these numbers already exist. Oh, we didn't write this other one down, by the way. The density of water. We very, very cleverly set that to 1. That makes our life supremely easy. Because what that means is if I have 157 milliliters of water, I have 157 grams. At 2,048 grams, then I have 2.048 liters. Completely convertible metric from one to the other. We've set density to be 1 for water. And anything larger than 1 is going to sink. And anything lighter than 1 is going to float. All right, so if D equals mv, what does V equal? Let's not do V. Let's start with it anyway. If D equals m over V, what does m equal? Going to be the D times the V. Now there's more than one way to do this. The modern mathematical way in school is to take a number and divide both sides of the equation by that number. And if you do that and you're happy with doing that, then just continue doing that. If you don't know how to do it, here's how we used to do it. My new question says I need m to be on its own. M is currently right here. So I have to move the v over to the other side of the equal sign. And anytime you take a number and you move it across the equal sign, it changes from either being below or above the line in the quotient. What do we call numbers that are above the line? Numerators. And numbers that are below the line? Denominators. So if you move a value across the equal sign, it changes from being a denominator to a numerator, or it changes from being a numerator to being a denominator. So m now equals d times v. Okay? We all need to know just a little tiny bit of algebra, just a little bit. So if d equals m over v, what does v equal? I gotta get v on its own. Currently it's a denominator. I just moved it up. That's why I made this one the second one, because this one I do mentally in 2 steps. That has to move across the equal sign because it's a denominator to make it a numerator. So I know that m equals d times v, and then to get v on its own now, I take that d and I move it across the equal sign where it goes to the bottom. So v equals m, oh, I almost wrote d, over d. All right, now, do I need to memorize all of these permutations? No. Is there something that I can do when I'm writing my calculation out to help me?
Yes.
What would that be? Write the units in. What's my unit for mass? Grams. And what's my unit for volume? Does grams per milliliter agree with the value that I'm expecting for density? Because density will probably tell you in the question. Give the answer in grams per milliliter what the density of this thing is. If you write the value of your units in your calculation, it leads you closer to not screwing up. Okay, mass. Your number's got to be in grams. Density is grams per milliliter. And volume is milliliter. So when we write that out, that's grams, milliliters, milliliters. Those milliliters cancel because there's one above. There's one above the line as a numerator and one below it as a denominator. They just cancel each other out. My answer's in grams. Leave the units in. Because at the end of the day, if you just write a number for an answer in a science class, if you write a number, you've answered half of the question. I need to know what that number is. Is it minutes? Is it miles? Is it dollars? I need to know what it is. Okay, volume is in milliliters. Mass is in grams. And we're going to divide grams by grams per milliliter. Okay, so the first thing that happens here is that the grams cancel each other out. And then the second thing that happens here is that if you divide any number by a number that's also divided by another number, that number ends up coming up to the top. Dividing by divider, dividing by something that's being divided, ultimately puts that number to the top. And I get my milliliters. Okay? The remaining stuff that's in this chapter tells us that matter exists in pure materials, but also in mixtures. And, we've got to do significant figures. We'll do a tiny bit of that when we come back, but otherwise, we're pretty much done with this chapter. No class on Monday, and we follow the lab rule in Concordia from chemistry is if there is no Monday lab, there is no Tuesday lab, Wednesday lab, Thursday lab. There's no lab activity, although you might have an in-class activity in the lab room, there is no actual lab. No class Monday, see you Wednesday. Oh, I forgot to bring it. I forgot to bring it.
Yeah.